This is SpaceTime Series 25, Episode 54. Coming up on SpaceTime, scientists recommending a new mission to study the planet Uranus, NASA's James Webb Space Telescope now in full focus, and some sad news with NASA and DLR announcing that the SOFIA flying telescope will be grounded for good. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers are recommending a new mission to explore the ice giant Uranus. The push comes thanks to a planetary alignment, which would allow spacecraft to slingshot there in 2031. Orbiting some 2.9 billion kilometres away from the Sun, between the orbits of Jupiter and Neptune, Uranus is unique in our solar system as the only planet to orbit on its side, literally rolling like a barrel. Because it orbits the Sun some 19 times further out than the Earth, astronomers have only visited Uranus once. That was very briefly in 1986 during NASA's grand tour of the outer solar system with a flyby by the Voyager 2 spacecraft. During the close encounter, astronomers were only able to see one side of the ice giant, which is a system of at least 13 rings and some 27 known moons. If approved, the mission would launch in 2031, using both Venus and Jupiter as gravity-assist slingshots to fling itself into a Uranian orbit, and yes, that is the way you say it, in 2043. The mission would include both an orbiter and a descent probe. The orbiter would spend several years flying around the planet, gathering observations on features such as its magnetic field, which is thought to power the planet's glowing aurora. Meanwhile, the descent probe would drop down into the planet's dense hydrogen, helium, water, ammonia and methane ice atmosphere, exploring what drives the planet's powerful winds. While the dwarf planet Pluto and the Earth's moon's south pole are both colder, reaching temperatures as chilly as minus 238 degrees Celsius, Uranus is the coldest planet in our solar system, with temperatures getting down to minus 224 degrees Celsius. Named after the Greek god of the sky, Uranus was discovered in 1781 by William Herschel, who originally wanted to name it George's star, after the British monarch King George III. The planet is some 4 times the size of the Earth and takes 84 Earth years to complete one orbit around the Sun. Uranus and its sister planet Neptune are thought to have been part of a group of 3 similar ice giants that formed beyond the giant planets Jupiter and Saturn. They're actually thought to have formed closer in towards the Sun than their current orbital positions, but they were gravitationally perturbed out to their current orbits as Jupiter and Saturn migrated outwards. During this migration, Neptune and Uranus swapped orbital positions, and the third ice giant in the group was flung out completely, either into interplanetary space, where it now exists as a free-floating rogue planet, or into the outer Kuiper belt or Oort cloud as the mysterious and yet-to-be-found Planet 9. Uranus is full of scientific mysteries, such as how it developed its highly complex magnetic field, which is tilted relative to the planet's rotational axis. And of course why it rotates on its side, tipped at an angle of 97.77 degrees. Astronomers speculate that it must have suffered a massive impact with another body sometime early in its history. Its many moons are also fascinating worlds, such as its 5th largest moon Miranda, which looks like a jigsaw puzzle that's fallen apart and has been put back together in a weird order, full of cracks and fissures and pieces that don't seem to fit together properly. Then there's Titanian Oberon, which are big enough to have water beneath their icy surfaces, and the strange pot-marked Phoebe and mottled Park. While most planets in our solar system have moons named after characters of Greek mythology, Uranus's moons are all named after characters from the works of William Shakespeare and Alexander Pope. Also, studying Uranus could provide fresh insights into many of the more than 5,000 planets now known to be orbiting other stars, the most common of which, some 40% in fact, are similar in size to Uranus and Neptune, making Uranus the most common planet design we know. This is SpaceTime. Still to come, the James Webb Space Telescope now in full focus, and the SOFIA Flying Telescope to be grounded for good. All that and more still to come on SpaceTime. NASA's James Webb Space Telescope is now in full alignment and ready for commissioning. After a full review by mission managers, the $10 billion observatory has now been confirmed as capable of capturing crisp, well-focused images with each of its 4 powerful scientific instruments. So, scientists have now agreed to proceed through to the final stage of commissioning the Earth-orbiting observatory, known as Science Instrument Commissioning. This process will take about 2 months, after which science operations will begin. James Webb Optical Telescope Element Manager Lee Feinberg from NASA's Goddard Space Flight Center in Greenbelt, Maryland, says the successfully aligned telescopes already delivered a series of remarkable test images. In fact, the optical performance of the telescope continues to be better than the engineering team's most optimistic predictions. James Webb's 18 golden hexagonal mirrors are now directing fully focused light collected from deep space down into each instrument. And each instrument is now successfully capturing images with the light being delivered to them. James Webb Wavefront Sensing Control scientist Scott Acton from Ball Aerospace described the test images as profoundly changing the way he sees the universe, with the Earth surrounded by a symphony of creation and galaxies everywhere. The image quality delivered to all the instruments is diffraction limited. That means that the finest of the detail that can be seen is as good as physically possible given the size of the 6.5 meter primary mirror. From this point forward, the only changes to the mirrors will be really small periodic adjustments to the primary mirror segments. So, now the James Webb team turn their attention to science instrument commissioning. Each instrument is a highly sophisticated set of detectors equipped with unique lenses, masks, filters, and customized equipment that helps it perform the science it's designed to achieve. The specialized characteristics of these instruments will be configured and operated in various combinations during the instrument commissioning phase in order to fully confirm their readiness for science. Though telescope alignment is complete, some telescope calibration activities remain. As part of scientific instrument commissioning, the telescope will be commanded to point to different areas of the sky where the total amount of solar radiation hitting the observatory will vary in order to confirm thermal stability when changing targets. Meanwhile, ongoing maintenance observations every 2 days will monitor mirror alignment and, when needed, apply corrections to keep the mirrors in their aligned locations. The James Webb Space Telescope is located in what's known as Lagrangian L2 position, a sort of gravitational well 1.6 million kilometers away from the Earth on the planet's night side. While the Hubble Space Telescope sees the universe in primarily visible light, only just dipping into the near-infrared and near-ultraviolet, James Webb will focus on the longer infrared wavelengths. This will allow it to focus on light from the very early universe, well beyond the 13.4 billion year limit of Hubble, back to a time when the very first stars and galaxies began to form. The physical expansion of space-time as the universe grows from the Big Bang has caused light from this period to stretch from the ultraviolet through the visible and now into the infrared. Closer to home, James Webb will also study the atmosphere of distant planets orbiting stars other than the Sun. This will be part of a search for chemical signatures in the atmospheres of these planets, which could be evidence of life beyond Earth. James Webb will change the way we see the universe, and it might also change the way we see ourselves. This is SpaceTime. Still to come, NASA and DLR ending operations of the SOFIA Flying Telescope, and we explore the constellation of Scorpius, the spectacular M6 and M7 open star clusters, and the Eta-Aquarids meteor shower produced by Halley's Comet as we tour the night skies of May on Skywatch. Some sad news today, with NASA and the German Aerospace Center DLR formally announcing the ending of operations of SOFIA, the flying telescope. SOFIA, the stratospheric observatory for infrared astronomy, used a modified Boeing 747 SP airliner equipped with a 2.5-metre reflecting telescope mounted in the rear section of the aircraft to undertake high-altitude infrared observations of the cosmos, flying on missions lasting around 13 hours at 45,000 feet. These missions measured magnetic fields in galaxies, spotted water on the sunlit portions of the moon, and detected helium hydride, the first type of ion to form in our universe. This report from NASA TV.
I think of SOFIA mostly as sort of catching light.
Day after day, we can get up and do these missions and really do cutting-edge astronomy in the infrared spectrum. SOFIA is an observatory, and like other observatories around the world, it can do a lot of different science. A lot of those observatories are on the tops of mountains around 13 or 14,000 feet.
Even when we have a ground-based telescope in a perfect place, sometimes it doesn't get any data because the clouds come in. Being able to fly over all of that is just a tremendous asset.
What happens is in the upper atmosphere of the Earth, as the light comes down, from some astronomical object, very little of that light is able to pass all the way down to the ground. So what SOFIA does is it flies above the bulk of that water in the atmosphere.
But SOFIA can fly at 43,000 feet, more than double the height of all of the other observatories in the world.
And that is above 90% of the water vapor, and that's a position that is necessary for astronomers to do infrared astronomy.
So space-based observatories have some really unique aspects to them. They're always in space, they're very cold, they can observe around the clock day in and day out.
The spacecraft, the demand on low weight, low power consumption are very extreme. So in an airborne observatory, you have a lot of power, a lot of space available.
We can carry instruments that are hundreds of pounds. We can give those instruments much more power than you can generate from solar collectors in space. We're not limited to the minimum weight that launch vehicles require to put something into space. We can fix those instruments day after day. The airplane comes home, we can repair them. It's very, very challenging to ever repair anything in space, and it's been done very, very few times.
So they're actually able to track a target as it moves across the sky as it's rising and setting. Not only does it have to be aware of time and position, but it's also got to be making the right motions across the surfaces of the Earth so that combined motions allow us to be able to lock onto the object over periods of a couple of hours. One of the powerful benefits that SOFIA brings us is the ability to go chasing these occultations in a way that no other observatory can do.
An occultation is basically a situation where a planet or an object of interest moves in front of a background star.
We observed a Pluto occultation, so that was where Pluto fell in our line of sight with a background star and made that star's light blink out very momentarily.
They modeled where that shadow was going to be, and we flew this airplane at roughly 500 miles an hour to catch a shadow that was going across the surface of the Earth at 53,000 miles an hour.
Simply by looking at the way that the background light blinked out, tells us something about the shape of the object, whether that object has an atmosphere or not, and you can even determine things like how the atmosphere's temperature and pressure vary from the ground all the way up to the top of that atmosphere on that object. You are limited as to what parts of the sky you can actually observe when you're in the northern hemisphere. So deployments out of our home base here in Palmdale gives us access to one half of the sphere. And when we go down to New Zealand, we'll have access to a whole new set of objects, a whole new part of the sky. Infrared astronomy allows you to peer into the core of really cold gas clouds where the stars are starting to form. Planets, comets, dust particles. So look at star formation in extreme regions. These things, because of their cold temperatures, happen to radiate most of their energy at these infrared wavelengths that SOFIA studies. SOFIA actually has several different instruments.
The science instruments receive the electromagnetic spectrum, the light, through the telescope.
Instruments mean cameras or photometers or spectrometers. The telescope without instruments is totally useless.
We have a whole team whose job it is to prepare the instruments and do a very precise movement, a choreographed movement of one instrument off the airplane, another one on.
Some of them make pictures that will look a lot like something that would have come out of a digital camera, but of course at a different wavelength. Others will not look like a picture at all.
One of the biggest challenges, of course, is we're putting a large hole in the side of the airplane.
The telescope in total is 17 metric tons, and there's an additional 3 tons distributed in electronic racks all over the aircraft.
The telescope has a certain level of precision. The instruments require a certain level of precision and accuracy in order to conduct the science. And the engineering challenge of providing that stability on an airplane that's flying and encountering turbulence is a significant challenge.
We had major structural modifications that had to happen. We had to add an additional bulkhead just forward of the telescope so that we can maintain a pressure area where people can work. And then the aft area is vented to the outside as we open the door.
The telescope is operated when a large door is open, so the environment is not very benign.
The telescope is something that is designed to free float. It floats on a spherical bearing, and that allows the telescope to be somewhat isolated from the movement of the aircraft. Inside SOFIA, it's like flying on any other airliner.
Planning for about a 10-hour mission, hopefully about 8.5 hours worth of science out of that.
We do pre-flight checks on all the airplane systems and all the observatory systems, fuel up the airplane. We go into a crew brief in the late afternoons where the entire team that's going to fly on the airplane gets together, talks about the objectives for the flight, status of all the systems, the weather, and the mission plan ahead. The team goes out, does their pre-flight checks on the airplane, start engines, we take off, climb to altitude, and do whatever mission's planned for that night. Usually it's about a 10-hour flight.
We know before we even get on the plane what objects are going to be looked at exactly what time in the flight they're going to be looked at. It's all sort of planned out and choreographed like a complicated dance routine.
SOFIA is a unique blend of aeronautical capabilities, science engineering in the form of a state-of-the-art telescope, and then cutting-edge science instruments.
We have the U.S.-German partnership, which is the 80% U.S. and 20% German.
We were responsible for developing and delivering and support the integration of SOFIA's infrared telescope.
On board, there's probably about 20 to 30 personnel, along with USRA personnel, our science support personnel, or mission ops.
We also have multiple NASA centers, NASA Ames, primarily responsible for the science, and NASA Dryden responsible for the aircraft operations. It takes that total group of expertise together that makes SOFIA an operational telescope.
Sometimes I think that my kids think science is done by some person sitting in a lab or up on a mountain with a telescope all by themselves. Having them see that it's really such a team effort, I think is important.
Using instruments from Germany does not mean that they can only be used by German institutions. So those instruments can be used also by US institutions, by other institutions.
This facility is not being built for NASA. We are providing it for the science community, for future scientists, and for educators. Through those teachers, there are Airborne Astronomy Ambassadors programs, and they'll be able to extend a lot of what we learn on SOFIA into the classroom.
SOFIA's science is driven by the demands and the imagination of the community.
The thing I get satisfaction over is seeing a team succeed themselves. And whether that be technicians installing electrical components or scientists getting the data that they receive, or a teacher getting a good experience on board to take back to their classrooms.
So SOFIA is considered to be an international resource to be used by the global community of astronomers.
The decision to ground SOFIA was contained in the 2023 White House budget request. SOFIA will finish its 8 years of service on September 30. This is SpaceTime. time now to turn our eyes to the skies and check out the celestial sphere for the month of May on Skywatch. May is the 5th month of the year in both the Julian and Gregorian calendars. The month was named for the Greek goddess Maya, who was identified with the Roman-era goddess of fertility Bonadea, whose festival was held in May. But I guess more importantly for many of our listeners, May typically marks the start of summer vacation season in the United States and Canada. Let's start our tour of the night skies by looking east, where you'll see the constellation Scorpius the Scorpion. In Greek mythology, the constellation was named after Scorpius, who was sent to Earth by the goddess Gaia in order to slay Orion the Hunter, after he boasted that he could kill all the animals on Earth. Scorpius stung Orion in the shoulder, but Orion's life was spared by Ophiuchus the Healer, and it was placed in the heavens along with Scorpius, who continues to pursue him for eternity. Orion the Hunter has become the hunted forever, with Scorpius rising in the east this time of year to triumphantly chase and defeat Orion, who sets in the west. Meanwhile, Ophiuchus the Healer rises in the east following behind Scorpius to chase and crush him into the earth as the Scorpion sets in the west. And so, this ancient story continues to play out in the heavens year after year. Interestingly, parts of this story predate the Greeks, with Orion known in ancient Egypt as Osiris, the god of the underworld and of regeneration. The brightest star in Scorpius is Alpha Scorpii, or Antares, the scorpion's heart. In ancient Greek, the name Antares means the equal or rival of Mars, the god of war. That's because its golden orange appearance is similar to that of the red planet, and it passes very close to Mars every 780 years. Easily seen with the unaided eye, Antares is some 550 light-years away. But it looks so bright because it's around 57,500 times as luminous as the Sun, and is one of the largest known stars in the universe. Antares is a red supergiant, about 18 times the mass and 883 times the diameter of the Sun. Were it placed where the Sun is in our solar system, it would engulf all the terrestrial planets, Mercury, Venus, Earth and Mars, and its visible surface would extend almost as far out as Jupiter. A light year is about 10 trillion kilometres, the distance a photon can travel in a year at 300,000 kilometres per second, the speed of light in a vacuum, and the ultimate speed limit of the universe. Astronomers believe Antares began life around 12 million years ago as a spectral type O or B blue star. Astronomers describe stars in terms of spectral types, a classification system based on temperature and characteristics. The hottest, most massive and most luminous stars are known as spectral type O blue stars. They're followed by spectral type B blue-white stars, then spectral type A white stars, spectral type F whitish-yellow stars, spectral type G yellow stars, that's where our Sun fits in. Then there's spectral type K orange stars, and the coolest and least massive stars are known as spectral type M red stars. Each spectral classification system can also be subdivided using a numeric digit to represent temperature, with 0 being the hottest and 9 the coolest. And then you add a Roman numeral to represent luminosity. So put it all together and you can describe our Sun as being a G2V or G25 yellow dwarf star, one of millions spread across our galaxy. Also included in the stellar classification system are spectral types L, T and Y, which are assigned to failed stars known as brown dwarfs, some of which were actually born as spectral type M red stars, but became brown dwarfs after losing some of their mass. Brown dwarfs fit into a unique category between the largest planets, which are about 13 times the mass of Jupiter, and the smallest spectral type M red dwarf stars, which are about 75 to 80 times the mass of Jupiter, or 0.08 solar masses. Like the similar-sized red giant Betelgeuse in the constellation Orion, Antares will almost certainly end its life as a spectacular Type II or core collapse supernova, probably sometime within the next 100,000 years or so. When it does explode, it'll appear as bright as the full moon for several months on end, and will be clearly visible during daylight hours here on Earth. Antares has a companion star, Antares B, located between 224 and 529 astronomical units away from the primary. An astronomical unit is the average distance between the Earth and the Sun, which is about 150 million kilometres or 8.3 light minutes. Spectral analysis of Antares B indicates it's pulling a lot of material off its bloated red supergiant companion. Located near Antares is the M4 globular cluster. Globular clusters are tight balls densely packed with thousands to millions of stars, which were either all originally formed at the same time from the collapse of the same molecular gas and dust cloud, or alternatively their galactic centers, the remains of ancient galaxies that have been merged into the Milky Way galaxy over billions of years. M4 is composed of 1 million or so stars originally born some 12 billion years ago. The M4 globular cluster is located some 7,200 light-years away, making it one of the nearest globular clusters to Earth. Easily seen through a pair of small binoculars, it covers an area of the sky as seen from Earth as big as the full moon. Astronomers estimate there are some 150 or so globular clusters orbiting in the halo of the Milky Way. Located near the tail of the Scorpion are two open star clusters known as M6 and M7. Open star clusters are loosely bound groups of a few thousand stars, which were all originally formed from the same molecular gas and dust cloud at the same time, but are not as densely bound as globular clusters. Open clusters generally survive for a few 100 million years, with the most massive ones surviving for maybe a few billion years. Now, in contrast, the far more massive globular clusters exert far stronger gravitational attraction on their members, which is why they can survive so much longer. M6, which is also known as the butterfly cluster, is some 12 light-years across and located about 1,600 light-years away. It contains around 80 stars, which are all less than 100 million years old, which is quite young in cosmic terms. The M7 or Ptolemy cluster is named after the famous Greek astronomer and mathematician Claudius Ptolemy. It's about 980 light-years away and is far more dispersed than M6, covering an area around 25 light-years across. And at around 200 million years, it's about twice as old. By the way, the M in terms like M4, M6 and M7 are abbreviations for Messier, in honour of the 18th century French astronomer Charles Messier, who developed an astronomical catalogue of fuzzy nebulous objects in the skies. See, Messier was a comet hunter, and he compiled a list of 103 fuzzy objects which weren't comets, and so from his perspective could be ignored. Later, other astronomers added additional celestial objects to the list, bringing the present catalogue up to 110. Our solar system, in fact most of the stars we see when we look up in the night sky, are located in the Milky Way galaxy's Orion Arm. The Orion Arm, also known as the Orion Spur or the Orion Cygnus Arm, depending on which name you prefer, is some 3,500 light-years wide and around 10,000 light-years long. The Orion Arm is named after the Orion Constellation, which is one of the most prominent constellations in the Southern Hemisphere summer and Northern Hemisphere winter. Some of the brightest and most famous celestial objects in the constellation include Betelgeuse, Rigel, the stars of the Orion Belt, and the Orion Nebula, all located within the Orion Arm. The Orion Arm is located between the Carina-Sagittarius Arm, which is more towards the galactic centre from our position, and the Perseus Arm, which is more towards the outer edge of the galaxy from our point of view. The Perseus Arm is one of the two major arms of the Milky Way, the other being the Scutum Centaurus Arm. Long thought of as a minor structure, a spur if you will, between the two longer adjacent arms, Perseus and Carina-Sagittarius, evidence was presented in mid-2013 that the Orion Arm might actually be a branch of the Perseus Arm, or possibly a completely independent arm segment itself. Within the Orion Arm, our solar system, the Sun, the Earth and all the other planets we know, are located close to the inner rim in what's known as the local bubble, about halfway along the Orion Arm's length, approximately 26,000 light-years from the galactic centre. The local bubble is a cavity in the interstellar medium in the Orion Arm, containing among other things the local interstellar cloud which contains our solar system, and the G-cloud. It's at least 300 light-years across, and it has a neutral hydrogen density of just 0.05 atoms per cubic centimetre. That's just 1/10 of the average for the interstellar medium across the Milky Way, and about 1/6 that of the local interstellar cloud. The hot diffuse gas in the local bubble emits X-rays, and is the result of a supernova that exploded sometime during the past 10 to 20 million years. It was once thought that the most likely candidate for the remains of this supernova was Geminga, a pulsar in the constellation Gemini. However, later it was suggested that multiple supernovae in a subgroup B1 of the Pleiades moving group was more likely responsible, becoming a remnant supershell. Our solar system has been travelling through this region of space occupied by the local bubble for the last 5 to 10 million years. Its current location is in what's known as the local interstellar cloud, a minor region of slightly denser material within the bubble. The cloud formed when the local bubble and another bubble called the Loop 1 bubble met. Gas within the local interstellar cloud has a density of about 0.3 atoms per cubic centimetre. From what we can tell, the local bubble isn't spherical, but seems to be narrower in the galactic plane, becoming somewhat egg-shaped or elliptical, and may even become wider above and below the galactic plane, becoming shaped more like an hourglass. And it's not alone, it's abutting other bubbles of lesser dense interstellar medium, including the Loop 1 bubble. The Loop 1 bubble was created by supernovae and stellar winds in the Scorpius-Centaurus association some 500 light-years from the Sun. The Loop 1 bubble also contains the star Antares that we spoke about earlier. Astronomers have identified several, well, I guess you'd call them tunnels, which connect the cavities of the local bubble with that of the Loop 1 bubble. Collectively, they've been referred to as the Lupus Tunnel. Other bubbles which are adjacent to our local bubble are known as the Loop 2 bubble and the Loop 3 bubble. Looks like astronomers still have a problem when it comes to thinking up cool names. Also visible this month is the Eta-Aquarids meteor shower, which is generated as the Earth passes through the dust and debris trail left behind by Halley's Comet. Comet P1 Halley is a well-known short-period comet which visits the inner solar system every 75 to 76 years. The 15-kilometre wide mountain of rock and ice will make its next close-up appearance in 2061. It's named in honour of the British astronomer Edmund Halley, who in 1705, after examining ancient Chinese, Babylonian and medieval European records, successfully predicted its return in 1758. However, he died in 1742, before his prediction could be confirmed. The comet's highly elliptical and elongated orbit takes it from between the orbits of Mercury and Venus out almost as far as the orbit of Pluto. Halley's orbit is in retrograde, meaning it orbits the Sun in the opposite direction to the planets, that is, clockwise from above the Sun's northern pole. This retrograde orbit results in it having one of the highest velocities relative to the Earth of any object in the solar system, travelling at some 70.56 kilometres per second, or if you prefer, 254,016 kilometres per hour. As well as the Eta-Aquarids meteor shower every May, Halley's Comet also produces the Uranus meteor shower in late October. Astronomers think Comet Halley was originally a long-period comet which took thousands of years to travel to the inner solar system from the Oort cloud, but was gravitationally perturbed into its current orbit by close encounters with the giant outer planets. The Oort cloud is a hypothetical sphere of comets and asteroids beyond the heliosphere, a mixture of vagabonds from the solar system and objects from deep space which have been collected by the Sun's gravitational pull. Occasionally, as the Sun passes by another star, an Oort cloud object will get perturbed and be flung towards the inner solar system. The Eta-Aquarids meteor shower runs from the 19th of April through to the 28th of May, peaking around May the 5th, with around 55 meteors an hour, making it one of the Southern Hemisphere's best celestial showers. However, back in 1975, they were running 95 meteors an hour, and in 1980 it was up to 110. Even better, the bright yellow meteors often appear as streaks known as trains. As their name suggests, they radiate out from the direction of the constellation Aquarius and the star Eta-Aquarii. Just look towards the east after midnight and before dawn for the best view. Jonathan Nally, the editor of Australian Sky and Telescope magazine, joins us now for the rest of our tour of the May night skies.
G'day, Stuart. Yeah, well, we're talking about the May night sky. So where I live, we're heading into winter at the moment, and on the other side of the equator, we're heading into summer. So where I am, it's pretty cold at the moment. It's getting colder and colder as each night goes on, which makes it a little bit difficult to sort of get the motivation to go outside just because of the temperature. But that being said, the stuff that we can see in the night sky in the middle of the year, particularly down in the southern hemisphere, is just tremendous.
Did you see the morning planetary alignment?
Yes, wasn't that great? Wasn't that tremendous? These things happen from time to time. There'll be a few little groupings of planets still coming up during the year, so we can talk about those. But yeah, that was really nice. All the planets in a row and everything. I remember back in 1989 or something, one of these typical things that come around about once a decade, the the psychics or the astrologers, whoever they were, said, "Oh, all the planets are going to line up in the one direction from the sun, and the gravity of all the planets are going to add up and pull Earth out of its orbit or change everyone's personality or whatever." And yeah, funny, I don't remember anything happening. Do you remember anything happening?
No, it was the same with the Mayan calendar reset. Absolutely nothing happened.
It's just anyway, that's not going to happen this year, fortunately. But anyway, lots of good things to see. So yeah, this time of year, if you can brave the cold in the southern half of the planet, at least, there's some great stuff. So the Southern Cross is the thing that most people want to see when they first start out. Other than the Saturn and the Moon and things. But the Southern Cross, this is the time of the year to see the Southern Cross, because the Southern Cross is up nice and high in the sky and it's standing upright for once and it's not laying over on its side. So you really can't beat it. The interesting thing with the Southern Cross area is if you've got good dark skies and you've let your eyes get adapted to the dim light, you're not staring into a street light or something, there's a couple of other things you can spot just near the Southern Cross. One of them is called the Jewel Box, and this is a little star cluster just off one edge of the Southern Cross. And if you can even just get a pair of binoculars, just an ordinary pair of binoculars, they don't have to be super duper ones, and have a look at this jewel box. You see this beautiful little cluster of stars, and they've got different colours. Some star clusters, the stars tend to be all the same colour, like a bluish white or just white or something. But
yellowy.
The jewel box is the jewel box is a nice little grouping of different coloured stars. There are about 100 stars in this cluster, but you won't see all of them because some of them are faint. But you'll see plenty of them anyway. That's about 6,500 light years away from us. Much closer, about 590 light years away. And just next to the Southern Cross, if you've got good dark skies and you've let your eyes adapt, you'll see a big dark patch, probably about the same size or a bit bigger than the Southern Cross, just to one side of it. And that's called the Coal-Sack Nebula, because if you have got dark adapted eyes, it really does look like this big black blotch right next to the cross. It's just a big interstellar cloud of gas and dust that's blocking the light of the stars from behind it. So it just seems like there's a big hole in space that you're looking through, but it's just a big gas and dust cloud that's blocking the light. To the right of the cross, as you're looking at it, to the right of the cross, we've got the constellations Carina, Vela, and Puppis. All of this is in the Milky Way, so there's lots of stars to see, lots of star fields and nebulae, these gas clouds that look really, really good. As I said, you can just use binoculars to have a look at them, but if you've got a telescope, even a small one, you'll get a much better view of quite a lot of these things. Around this area, in the constellation Centaurus, which is just nearby, a couple of really good things to see, which you can make out with the naked eye, but you can't make out what they are. You can just see that they look like a little fuzzy star thing. Or a big star cluster called Omega Centauri, which has 10 million stars, and it's about 17,000 light years away. And there's a galaxy you can see too. You can just make it out. It's bright enough to be seen with the naked eye. It just looks like a little fuzzy star. Get a pair of binoculars onto it. It looks like a tiny little fuzzball, and get a telescope onto it, and you'll see there's a big galaxy. This is called NGC 5128, and it's about 10 to 15 million light years away. Both of them not very far from the Southern Cross. Over in the west, after the sun has set, of course, you'll see the constellation Orion, the Hunter, going down in the west. That's the indication that summer is definitely over and the summer constellations are disappearing. So winter is coming on for us in the south, at least. Nearby, you've got Sirius, the brightest star in the night sky, and it's the brightest star in the constellation Canis Major, or the Greater Dog. And a little bit to the north of that, you've got another fairly bright star. This one's called Procyon, which is the brightest star in Canis Minor, the lesser dog, the smaller dog. Northern half of the sky for us down here in the south, if you look north, doesn't seem to have many bright star fields this time of year, at least in the evening time. There are some famous constellation names up in that part of the sky. You've got Leo and Cancer and Virgo, because that's the sort of area where the zodiac goes through. But amateur astronomers really like Virgo because even though you can't see it with the naked eye, when you get a telescope into this area, you can find hundreds and hundreds of galaxies. It's really good galaxy time of the year for people who like to get out, brave the cold, rug up, get your cold weather gear on, and go and have a look. Of course, if you're on the other side of the equator from where I am, if you're up in the north, still great to see Virgo. Good time of year. It's coming on the warmer weather, even better. So they've got it lucky, I suppose. If you wait a few hours until around midnight, you'll see some big, mighty constellations starting to come up over the eastern horizon. And the ones I'm talking about particularly are Sagittarius and Scorpius, which some people call Scorpio, and there's another one called Scutum, and there's one called Ophiuchus. Ophiuchus is this very large, dim constellation that technically is the 13th constellation of the zodiac, because the path of the sun through the sky just clips the corner of this constellation. So there are actually 13 constellations in the zodiac, but they tend to overlook that, don't they? Anyway, this area, Sagittarius, Scorpius, it's the heart of the Milky Way. Get some binoculars onto it, get a telescope and have a look if you can. And you don't need giant binoculars. You can get giant binoculars for astronomy, and they're really good. You need to put them on some sort of mount to keep them steady and look through them because they're very heavy, very, very heavy. But a normal, ordinary, basic pair of binoculars are 7x50s. The 7 means that's the magnification, 7 times magnification, and 50 is the measurement in millimeters of the lens at the front. There's the 2 lenses at the front of the binoculars. 7x50s are just a good all-round pair of binoculars. I've got a pair of 10x50s. So they're a bit bigger. The lenses are the same width, but the whole thing's a bit bigger because it's got to give you 10 times magnification. And it's probably just a little bit too heavy to hold for ages and ages and ages. So I tend to prop myself against something or rest the binoculars on something to point it at the sky. So you don't need giant binoculars. So don't think you're going to go out and spend lots and lots of money. Just a pair of 7x50s or 8x30s even is perfectly fine. See what's happening with the planets. Now, we'll start in the innermost part of the solar system with Mercury. Mercury, unfortunately, too low to see in the sky easily this month. Theoretically, you can see it really low on the horizon after the sun has set on the western horizon, but usually there are trees and houses and things in the way because it is really, really low down. So don't even bother, that's my advice. So wait until later in the year, August and September. We'll get a really good view of Mercury then. Venus and Jupiter can be seen in the eastern half of the sky in the hours before dawn, and they'll be quite close together for a lot of May, so they should be pretty easy to spot. I mean, they will be the 2 biggest, brightest things in the night sky out there other than the moon. So Venus will be the brighter of the 2. That's because even though the planet is far, far smaller than Jupiter, like Earth is, Venus and Earth are roughly the same size, even though Venus is far smaller than Jupiter, it's much, much closer to us. Jupiter is a long way away, Venus is closer, and Venus also has these very highly reflective whitish clouds that cover the whole planet. Jupiter is covered with clouds, of course, too, but they're sort of not as white, so they're not reflecting as much sunlight, and, of course, it's much further away. Mars is in the morning sky as well, out to the east. Take a look in the last few days of the month of May, 28, 29, 30, 31, and you'll see Mars very close to Jupiter this time. They'll be less than a degree apart on a couple of those days, which is fairly close, so that should look pretty specky. Jupiter will be brighter than Mars. And finally, the other bright planet, Saturn, it's rising around about midnight this month, little after midnight at the start of the month, around about midnight, middle of the month, and just before midnight by the end of the month, getting earlier each day. See if you can take a look at Saturn through a telescope if you can. Maybe you've got one, or a friend's got one, or a neighbour, or astronomy club, or an observatory nearby, because there is just nothing else like looking at Saturn through a telescope and seeing its rings. Jupiter, Neptune, and Uranus all have rings as well, but you can't see them through a telescope. But Saturn you can, so get a hold of it and now have a look. Because the other thing too with Saturn is that there's this regular pattern we go through of just because of the angle between us and Saturn, because the orbits of the planets are not in a perfect flat plane going around the sun. Some are a little bit above that plane, some are a bit below. And what that means is that when we look at Saturn, sometimes the rings are tilted quite a big angle to us so we can see them easily. And other times the rings are not tilted very much and it's bit hard to see. And in fact, there are times when the rings are exactly edge on and they more or less seem to disappear. So we're heading towards that in about 5 years, I think it is, 5 or 6 years or so. So the rings are tilted about 14, I think they're 14.5 degrees at the moment, or 15 degrees, something like that. And that's going to get less and less as the next few years go along until we get to what's called crossing the ring plane. From our point of view at Earth, looking out into space, Saturn's rings will be edge on, which is also quite interesting to see because Saturn's rings appear to disappear, if that makes sense. But they certainly look much better when you can see them, if that makes sense. And that, Stuart, is the May night sky.
That's Jonathan Nally, the editor of Australian Sky and Telescope magazine. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.